Hello, in this video we want to look at section 9 from chapter 7. It's all about world energy use. Before we get going, I kind of want to hit these terms, work, energy, and power, just so that we all know what we're talking about as we get going. Work we've seen, so work is just a force over a distance. So we're kind of familiar with that by this point. So some amount of newtons over some distance. The unit for work is 1 joule, which would be 1 newton applied over 1 meter. So that's work. And if we want to talk about energy, it's very similar. Energy is just the how much work something can do. Okay, so it'd be the amount of work. Energy is just an amount of work. Okay, so we still talk about it in joules. We still talk about energy in joules, and so that can be any form of the ability to do work. So say nuclear energy, chemical energy, kinetic energy, magnetic potential, heat energy. They're all just forms of an ability to do work. Okay. Power is just a little bit different. When we say power, we're talking about the rate at which energy is transferred, and so it would be joules per second for power. So it's very closely related to energy. It's just how much energy can be transferred in a given amount of time, and the unit for that would be watts. So joules per second is watts. There is a conversion for watts to horsepower, so they are very similar concepts. So just so we all know what I'm talking about if I use these words. The law of the conservation of energy, we need to talk about that. Just says that energy cannot be created or destroyed. So what that means is, no matter what we do with the material we're working with, the net energy is going to be the same. So if I have a log, say it's a couple of pounds, and I burn it, then all of that energy is still around somewhere. Okay. This becomes really important when we talk about trying to, say, generate electricity and have electrical energy. Now, if we're burning coal to do that, we're not going to get all of that energy out of the coal. Some of it is going to be lost. And this is where we kind of talk about efficiency, which is the amount of useful energy that we get out of a energy source divided by the total energy input. Okay, so a lump of coal that we might burn is going to have way more energy in it than we can get out as electrical energy. Okay, some of it's going to get lost to heat, some of it's going to be left in the byproducts, some of it's going to go off into the atmosphere as gases from the combustion process, and only a portion of it is going to be usable electrical energy. Okay, so efficiency, when we talk about that, it's the amount of useful energy or work that we get out of a process divided by the amount of energy we put in. Okay, so that'll come up again later. Some kind of common things that we might see that we can compare the efficiency of. So a lot of these kind of physical activities don't have a great efficiency. Okay, you can see that cycling is about 20%. About 20% of the energy that you have to put into cycling actually comes out in the form of, what's moving you on the bicycle. The rest of it gets lost. And you can kind of look down this list, pause it if you want to have a closer look, but a lot of these are not very efficient. Okay, here's the electric motor. Definitely is very efficient. That's one of the selling points of electric vehicles, is that the motor itself is very efficient. Now, when we're generating electricity, a lot of our methods are not very efficient, so you've got to kind of look farther down the chain. But the motor itself does a very good job of converting the electricity that comes in into movement coming out. Okay, so a couple of examples. We've got our coal power plant here. Like I said, not very efficient when we compare the amount of energy that goes in versus what actually comes out as electrical energy. A lot of that gets lost. So getting on to the actual world energy consumption, here's a little pie chart of our current, well, almost current, 2006, but close enough, our current energy usage, and it's a little bit distressing to see how much of this is fossil fuels. Okay, we've got petroleum over here in green, coal in blue, and natural gas in the purple there, and that's a very large portion of our energy usage right now. The more kind of sustainable and what's the word I'm looking for? Anyways, renewable. The more renewable energy counts for a much smaller portion. So hydroelectric and nuclear are definitely the biggest chunks here, and then a smaller percentage for some other renewable energy sources. The reason this is important, of course, we all know this. The fossil fuels, we are using them faster than they regenerate. So, and of course, there's a lot of argument as to how quickly we're going through that supply, but it's not arguable that we're not going through it faster than they're getting made. So we want to. There's kind of a global push to work on expanding these renewable energy sources, so that we're not quite so dependent on fossil fuels. This table out of the book here, we kind of look at energy usage over the last several years here. Definite trend, more energy use as time goes on, and the scale on this is just massive. Okay, joules times 10 to the 18th power, just massive scale, and this is for the entire world energy consumption. So we can see it's been projected out. Here we are, close to 2020. And the projection is just that it's just going to keep increasing. So we definitely don't have any foreseeable future where our energy needs will decline. With the talk of needing other energy sources, there's kind of a table here that we'll talk about a few of these. They're just the amount of energy available or in a given object or event. So at the very top we've got the Big Bang. Absolutely massive amount of energy, just there for scale, really. If we come down to not very far down the list, we've got the annual energy usage of the world. So we're going to come back to that. We'll use that for a few things. And then notice that we've got some different types of bombs and fusion, okay, generating power with fusion and fission. So nuclear power, and if I go to the next page, you can see some more kind of small scale energy capacities here. So say 1 gallon of gasoline, 1.2 times 10 to the 8th joules, and if we compare that to the daily home electrical use, notice they're only about 10 times more, which should be kind of surprising. Okay, that 1 gallon of gasoline could power 10 homes for a day. That is if the efficiency was 100%. If we were able to harvest all of that energy out of a gallon of gasoline. It shouldn't surprise you that we can't. Okay, even say in your car, we're not going to get a very high efficiency. There's a lot of that energy lost. A lot of it just goes right out the tailpipe. Okay. And a lot of it is lost to heat also. Kind of have another look. So, say 1 gram of fat. If we have 1 gram of fat, it's got 3.9 times 10 to the 4th joules, which is a lot. Okay, compare that to gasoline. We've got about, what is that, 10,000 grams of fat to equal the energy in 1 gallon of gasoline. So just a little bit of comparison there in what's available. Not necessarily what we can harvest, but what's available in a given object. If we want to look at one example here, we've got the energy in fusion bombs were used to supply the energy needs of the world, how many of the 9 megaton variety would we need to supply a year's worth of energy for the world? If we go back and look at our table from before, we've got annual energy use at 4 times 10 to the 20th joules. So that's for the world. And then if we look at the 9 megaton fusion bomb, 3.8 times 10 to the 16. Okay. And so if we want to know how many of those bombs it would take to power the entire Earth for 1 year, we can just divide these. If we do that, see what we get here. So 4 times 10 to the 20th divided by 3.8 times 10 to the 16th. And we can see it would take roughly 10,500 of these fusion bombs to provide energy for the world for a whole year. Now, again, I'm going to keep saying it, that is if we could harvest all of the energy out of all of those bombs. Okay, if there was none lost to heat or byproducts or anything, if we could harvest all of that energy and make it useful, it would take about 10,500. Now, it is possible to harvest a lot of the energy, maybe even most of it, by detonating these underground and being able to harvest it that way. But even so, say there's 30,000 of these bombs existing in the world, complete guess, but even if there is, and if we could harvest all of that, that would only be 3 years worth of energy, and that's not even taking into account how much energy it might take to create one of these. Okay, so a somewhat more hopeful example is if we could use the hydrogen fusion energy of water. Okay, fusion energy is something that is hoped to be viable here within the next century, and just to kind of put it in perspective, we'll go back to that table again and have a look at the energy available in all of the Earth's oceans, which is 10 to the 34th joules. So I'll write that down. So 10 to the 34th joules. And if we again look at the world energy usage, 4 times 10 to the 20th. Okay, so if we want to compare the amount of energy available in the oceans versus how much energy the world is actually using, and it's kind of a massive difference, so we're just going to look at 1/1,000,000th of the available energy in the oceans. So if I just want 1/1,000,000th of that, I can just divide by 1,000,000, and that would be 10 to the 28th joules. Okay, so just 1/1,000,000th of the fusion energy available in the ocean, and we can get 10 to the 28th joules. If I divide these, so 10 to the 28th by 4 times 10 to the 20th, if I do that real quick, you can see we get an answer of 25 million. So there's 25 million times more energy in 1/1,000,000th of the hydrogen fusion energy available in the ocean than it takes to power the world for a year. So if we could just harvest 1/1,000,000th of that energy that's available, we'd power the world for 25 million years. Put that in perspective a little bit. The earliest humans kind of dated back 3 million years ago. Okay, and of course that's a current projected energy usage that might go up, but it kind of puts into perspective how important the quest to get to make fusion energy a viable option. So anyways, kind of just an overview, a very rough overview of kind of the scale of world energy usage compared to some other things. Thanks.